morning, everyone. I'll bring your attention back to a bit from agriculture, overall economic, circular economy, and back to the wastewater system. So I think the whole conference talked about circular economy, and yes, indeed, we have shifted our focus from nutrient removal in the past decade now to the circular economy. We try to recover as much of resource as we can, including the wastewater is basically, most of the wastewater is water. Definitely we have some cellulose and solids after we remove that, but mainly it's just the nutrients, mainly nitrogen, phosphorus, of course, a lot of carbon. So when we try to recover those, we try to recover water, and we try to convert the carbon into energy, and of course, we try to get the rest of the nutrients into other materials. So that's the shift towards circular economy we talk about in urban wastewater management. And when we try to do this circular economy, recover all the resource, we also consume a lot of energy associated with that. Not just to remove this little pollutant trying to recover, but also in the meantime, we generate a lot of greenhouse gas. So later on, I will introduce what are the greenhouse gas we particularly talk about in the wastewater industry. So wastewater currently is contributed as the 7th or 8th largest GHG emitters. But this is debatable because a lot of accountings and also calculations from our GHG emissions are not as accurate as we thought. So what are the net zero? Definitions is when we look at greenhouse gas emissions, we not just look at the carbon. We all know it's CO2 equivalent. So when we look at CO2 equivalent, we converted all the greenhouse gas based on their global warming potential. So if we treat CO2 as one, and the CO2 equivalent for the methane, which is multiplied by 28. And the other one, which is very common from wastewater, is nitrous oxide. That's part of the nitrogen removal process. We generate nitrous oxide. So we have to multiply by 265, newest number maybe 273 into CO2 equivalent. When we want to get net zero, we have to make sure all these add up. CO2 equivalent is offset or balanced by the carbons being removed by organization. So water industry, normally we have to obligated report two scopes. So there are 3 in total, but we obligated report scope 1 and scope 2. So scope 1 are the direct emissions that is generated during the process, including some of the fossil CO2, including methane, including nitrous oxide. And also scope 2, it's here, which is indirect emission. That's really related to any of the energy consumptions that is generated from fossil carbon. And scope 3 are not obligated for water utilities report, but it's really related to the supply chain. And the upstream chemical we use, if we build a new plant, and the cement we use, that's embedded carbon. And also for the downstream, any solids we generated want to apply to agriculture, then the additional generation about emissions from those things coming from the wastewater treatment plants, that's also scope 3. Utilities have been put a lot of efforts trying to quantify scope 1, scope 2, even scope 3. I know Sydney Water has done a lot of work in scope 3 area, and among with those, I think scope 2 is relatively more straightforward because you have a clear record of how much energy you are using. And then scope 1 is the most challenging because it's fugitive emissions. You have to monitor where you emit and how much you emit. And those are more dynamic. So water widely, there's a net zero risk to zero campaign. So about 87 utilities has been signed up on this. And also we have, I think Australia, 14 utilities in Australia also signed this risk to zero. So that's the Australian campaign. However, what I want to mention is all those, it looks like a lot of utilities signed up, that only serves 3% of population in the world. So we still have a long way to go. All right, so let's have a look about Australians' utilities risk to zero, how the journey looks like. So this example from SA Water, So they have quantified using the National Greenhouse Gas Carbon Accounting Guidelines, we call it NINGAS, to estimate the general Scope 1, Scope 2 emissions. So you can see this is, well, on the pie chart, shows before 2020, well, majority of those, the gray columns, are contributed by the electricity consumptions. That means it's dominated by Scope 2 emission. And after that, after 2020, and gradually, you see the big reduction of the gray bars. That means SA Water is trying to take actions to reduce this fossil-generated electricity usage. So they try to get more renewable energies. And then you can see Scope 2 emissions relatively reduced. Easy for utilities to take actions. However, the remaining big chunk part is actually the remaining are the green ones. The green columns are really the fugitive greenhouse gas emissions. Some of the fossil uses generate CO2, but then that's dominant with their emissions. And also you can see it is almost flat, because these are estimated based on a fixed number of the emissions. So those increase really based on the population increase in the future years. The other example from Icon Water, which is the major utility in Canberra, the difference is they have been achieved 100% renewable energy back to 2020. So you can see that the gray part, which is the Scope 2 emissions, become zero. And all the rest dominant part majority are the dark blue, which is here's fugitive emissions. That's mainly methane, nitrous oxide. With the rest, a bit of the fuel consumptions, which generate the fossil CO2. So you can see with utilities they are facing is really the fugitive emissions. That's the big chunk part if they want to achieve net zero. And then when I move to what are those emissions associated with the Scope 1. So starting from the carbon cycle. So for utilities, the CO2 really embedded like in the wastewater. Most of these are coming from the carbon cycles. That's through the consumptions of human when we eat all this food, and then that's the normally CO2 coming to the wastewater. So through bacterial respiration, they go back. So if we close the whole cycle, that's biogenic CO2. That's not part of the emissions we need to worry about. However, we try to now generate biogas, or in some of the treatment process, there are a lot of anaerobic conditions. During the sewer transportation, during the anaerobic treatment, there are methane being generated. Or when we try to promote more biogas generations through the CO2, we also generate methane. And if the methane is not captured, but then released, so we interrupt this carbon cycle, that become part of the Scope 1 emissions. So we have to be careful about this. The other part is the fossil carbon. So you remember the little bit sort of remaining part of Scope 1, that is from the fossil fuel consumption. That's where if we are using any of the diesel engines on site to produce electricity, then this CO2 is part of the Scope 1. And also if we dose any of the carbon to enhance the nitrogen removal, but the carbon we dose is coming from a fossil product. For example, the fossil methanol, which is very popular product we dose to enhance denitrification. That's also become the CO2. Fossil CO2 goes into the Scope 1. Same as the nitrogen cycle, if we do complete nitrification, denitrification, very happily, everything convert into dinitrogen gas, then there is no greenhouse gas. We complete the whole cycle. However, we do generate nitrous oxide through the whole biological nitrogen removal process. And then that's also interrupt our nitrogen cycle. So it becomes nitrous oxide. And then because of the huge global warming potential, it becomes a big trouble for Scope 1. So when we look at the Scope 1 emissions, especially for methane and nitrous oxide. So we start from nitrous oxide. Nitrous oxide is mainly, because it's a big chunk, mainly from the secondary treatment where you have nitrogen removal happen. Or if you have aerobic digestions where you have also nitrogen removal process happen, that will contribute nitrous N2 emissions. The other one is sludge incineration. We do try to, some of the utilities try to burn all the sludge, or even through some of the gasification, those thermal cycles may also generate nitrous oxide. So compared with N2O, methane, as you can see, almost everywhere here. This is because during the transportation, we already have a lot of CO2, COD converted into methane, and then that may be emitted during the transportation. And the rest of dissolved methane will be transferred as long as there are gas-liquid transfer, they will emit it. And also majority may be emitted when the wastewater first heat into aeration process. The other major part is really the sludge side. Sludge side actually contribute majority of the methane emissions. Okay, so how these interact with our circular economy, with resource recovery. So wastewater, when we try to treat the wastewater, when we try to recover from all the resources from wastewater, if we look at, well, if we don't recover anything, these are influent, effluent. So if we try to recover water from it, normally for any of industry use or potable use, we have to through membrane process. And we all know membrane process, normally you need a lot of additional energy. And if you use energy that is coming from fossil CO2, then you basically increase your scope 2 emissions. So you try to you will make a higher energy input, increase your scope 2 emissions. Then the next is when we try to generate energy from any of the carbon source from our system. So we may directly increase the methane emissions through either leakage. Leakage is a big chunk part of methane, or we may interact with N2O generation by taking out of the carbon. I'll give an example to further explain. So that may directly increase the scope 1 emission. We try to recover more energy. The next is when we try to get more materials coming out. If we dose more chemicals or use any other chemical-based process, we may also potentially increase the scope 3 emissions. So use some examples, look at particularly how these may interact, the emissions interact with our recovery process. So with water reuse, so this is a pilot study, not by me. This is by Sweden. So they have running the pilot, large pilot scale, mimic the secondary, tertiary, and also the resource recovery with water potable reuse process in different process. And then they use the span as a case study to scale up all the pilot results. So what they found is if we try to recover water, you can see with any of those ultrafiltration membrane use, electricity is become the dominant CO2 equivalent contributor through the process. And that is understandable because once you have membrane process to recover water, definitely for span, majority of the electricity is coming from fossil carbon. But if in Australia, if we do have all this renewable energy, then this will become very minimum, so that's doable. So when you try to recover water through membrane process, the energy use source is really something you need to consider with the scope 2 emissions. And in terms of energy generation, so this is example of methane loss. So this is study did in Denmark. So they have used the ground-based sensoring technology, which is at a remote point, they monitor the overall plant emissions using a remote sensor. So they quantify the total emissions from the whole plant. So they did 23 sites where they have biogas generation facilities. So many, including both agricultural biogas plants and also wastewater plants. So you can see this is the loss that they have detected. Of course, they say higher methane loss coming from wastewater treatment plants than agricultural plants. But there is average quite a high about leakage happen. So overall, 81% methane leakage they quantified were released from the sludge treatment. So with the other figure, which shows percentage of loss of methane, which contribute to the total emissions or carbon footprint of the plant. So overall, you can see about 5% methane loss that can offset all the benefits that you're trying to use energy, renewable energy to offset the fossil carbon generated energy. So that gave us a signal. It's very good we generate biogas or energy from our treatment plant. But if we have a 5% methane leakage from that, that's basically offset all the benefits when we try to offset or use the energy we generated from the bio. So we have to be careful with that when we try to look at energy recovery from all the biomaterials. Okay, so before that, I want to mention the reason that is methane leak a lot. One of the reasons is because the anaerobic digester we use, we do have a lot of floating hood type of anaerobic digester being used. That's one of the big source. The other thing is just the pressure relief valve for safety. That's also become identified as a hot spot for methane release. So those simple things, we can later on consider simple engineering solutions that we can help to stop of leakage. That's going to be brilliant when we look at the energy recovery. Okay, the next thing I want to talk about is really the interactions between energy recovery and then also the later on nitrogen removal. So because the carbon, when we try to promote more energy recovery, however, in our currently existing plant, this carbon are also very valuable for nitrogen removal. That's where we need for the denitrification process. So there is a competition between how we utilize the carbon. Do we want to generate more energy, or we want to better reduce the nitrogen removal? So without looking at N2O part, I think as long as we meet the percentage of removal, that's okay. But now there's a different angles because we have the N2O generation. So this is a case study that we did in Victoria, in Melbourne. So this is a 4-step. How this works is the wastewater first come into from an anaerobic lagoon that is used to generate biogas, and then the biogas is captured. After that, this was sent to a 4-step feed treatment process. I probably will not go through how that works, but basically the flow was split into different steps. Beginning, normally the first one have 40%, and then later on reduced. Later on, the fourth is only treat 10% of the wastewater. So that's called a step feed. We try to remove nitrogen by steps. So what we are doing is we are trying to capture all these greenhouse gas emissions in this treatment plant during the nitrogen removal process. So this is quite small. These little dots, you can see, those are the hoods we put on. So it is quite small. I do have a video. So this is the treatment plant from anoxic zone, aerobic zones, and then with the aerobic zones, we capture the off gas using the floating hoods. And then those gas was sent into this centralized analyzer, so we can capture all this off gas, methane and N2O online. Okay, so what we have done is we have captured or calculated all the methane being captured and generated use energy, and also we collected all the scope 1, all the N2O methane emissions in the following stage, and also with the energy use being used for aeration. So we did consider them, converted them into the emissions. So these ones, the green ones, is basically the energy recovered through the from the biogas. You can see that is sort of more or less offset the purple one. The purple is really the energy being used following on for aeration. So that's more or less offset all the energy being used for the treatment plant. However, the leftover blue ones are really the scope 1 emissions. So the scope 1 emissions is dominant. So some of the methane is stripped out, but it's dominant by nitrous oxide, because with all these N2O, we have to multiply by 273 when converting to CO2 equivalent. And then when we look at distribution with the 4-step, so you can see majority of those. So these ones, this yellow and this blue is contribute 60% of the emissions. This is actually the later stage of the treatment. And then later stage, only treat 10%, 20% of the wastewater. And when we look at the details, you can see the N2O, the off gas is coincidentally very similar with the dissolved N2O from anoxic. That means it's all, majority of it is coming from the anoxic zone. And then that is coming the denitrification pathways. So I do not expect you to understand all these pathway generations. I just want to talk about, so this is where the pathway contributed majority of the N2O generation. And then that is coming from the carbon, where the denitrification of the carbon is limited because we don't have enough carbon for denitrification. And that is where the nitrous oxide is being generated and then later on stripped out. So this is really give us an example that how our energy generation may also play a role affect your following up nitrogen generation as well. So this is uncertainty with N2O emission. As I mentioned at the beginning, the N2O is really a big chunk there with uncertainties. So this is a recent published paper by Princeton University that they are highlighted the wastewater N2O coming from this sector may become the second largest source from the global sector after the agriculture. Okay, so as N2O is a big chunk, so some of this, if we take nitrogen out prior all this wastewater coming to the treatment plant, this may be a good thing. Like the urine recovery decentralized. If we take some of the nitrogen from this wastewater before they hit into our treatment plant, this will potentially reduce the direct nitrogen and N2O emissions. And also because the carbon need to use to reduce the nitrogen, then we may also enhance our energy recovery. However, when we also treat the urine, we also need to be careful because that's a centralized nitrogen stream. And if you directly treat it as biological, you may generate more N2O because of high nitrogen loading, also low alkalinity. So dealing with the resource recovery from the urine also need to attract additional attention. How we better look after resource recovery from this centralized stream. Okay, so this is second last slide of my talk. It's really, I want to highlight the interactions from the wastewater sectors with the rest. So Gordon had a lot about the agriculture interactions. So the biosolids go to agriculture, they definitely interact with the agriculture sectors. The other thing with the food waste, I think we try to generate biogas now, taking a lot of other food waste or other waste from other sectors. So this is good. We help to try to generate more energy. However, we also need to be careful that when we take out the carbon from everything we take into the system, with the leftover, all this digested liquor, the nitrogen stream, that we have to look after how we can remove those in our existing treatment plant. As mentioned, if we got too much nitrogen coming, we take already the carbon from it, we will also be suffered with the later on N2O emissions. The other thing is the energy sector, so we now try to interact with the hydrogen generation using the wastewater, treated wastewater. So that's very good because hydrogen renewable energy that can help us offset a lot of scope 2 emissions. And also with the leftover pure oxygen, we can also think about how that can better help us to achieve our circular economic goals and also reduce the emissions. The other thing is really with the chemical we use. So that's, although not direct from the water utility, but it's scope 3. So we do have an influence to choose more green chemicals when we try to use these chemicals to achieve circular economy. So overall, net zero is not conflict with circular economy. It's just to put another angle. How do we better achieve the circular economy goals when we try to also minimize the overall greenhouse gas emissions? So I only touched a few about examples of our resource recovery. Indeed, there are more valuable resources that can be recovered from the wastewater sectors. So I do hope that the new technology can be further developed, and also when we look at the resource recovery, we together look at also economic and environmental impact as well. So overall, we are in a very tight time to achieve the goals to reduce our greenhouse gas emissions. So we need to have this in mind that we have to really reduce the greenhouse gas emissions while we achieve the circular economy goals. Otherwise, we may not meet the target to achieve or to tackle the climate change. We will have a conference in Brisbane next month. next month. Today, 30th of September, actually November, not next month. So this is about nutrient recovery in the net zero era. So if you are around, we do welcome you to come to Brisbane and join this IW conference as well. That's all. Thank you very much.